Episode 3, Wired World, Connecting People with Code, from Telegraph to Internet. Picture a world where news travelled no faster than a galloping horse. Then, with a few electric pulses, everything changed. In this episode, we explore how code and technology linked humanity, wiring the world from the first telegraph click to the global internet. It's a saga of beeps, flashes, and packets, with each breakthrough bringing us all closer together. Get ready for surprising facts. Did you know the first transatlantic message took only minutes in 1866, when previously it took 10 days by ship? Or that the very first internet transmission crashed after just 2 letters? Let's plug into the network's origins. Segment 1. The Victorian Internet, Telegraphy. In May 1844, the world got a glimpse of instant communication. Samuel Morse sent the famous telegraph message, "What hath God wrought?" from Washington, D.C. to Baltimore. Those words, converted to dots and dashes, travelled 35 miles in mere seconds along copper wire. For context, prior messages took hours or days by horse or train. This was nothing short of miraculous. A Victorian internet of sorts. Morse's code, the encoding system of short and long signals for each letter, turned language into pulses of electricity and back again on the other end. Soon telegraph lines webbed countries and then crossed seas. By 1866, a durable transatlantic cable lay on the ocean floor, and for the first time Europe and America were in constant contact. Imagine the awe. News that once took weeks by ship could now hop across the Atlantic, almost instantaneously. Newspapers could print overseas headlines within the same day. Merchants could arbitrage prices between London and New York in real time. One newspaper marvelled in 1866 that America has been in direct communication with Europe since Sunday last. It was as revolutionary as the advent of the smartphone in our time. Of course, getting there was arduous. Early transoceanic cables snapped or failed. The first attempt in 1858 carried a few messages over a slow link before dying. But persistence paid off. The 1866 cable was a triumph of engineering, and importantly, of coding. Operators had to optimize Morse code transmission speed and use chemical devices to amplify weak signals over 2,000 miles of cable. The effect on global trade and diplomacy was immediate. Markets synchronized, and empires tightened control over far-flung colonies thanks to the telegraph. Victorian newspapers even dubbed this new interconnectivity the annihilation of space and time. Did you know? The telegraph's dot-dash code inspired other communication codes. In the 1890s, Guglielmo Marconi harnessed Morse code for the first wireless radio transmissions. Ships at sea, previously isolated, could suddenly send distress calls. Famously, the Titanic's SOS in 1912, sent via Morse wireless, alerted ships hours away to come rescue survivors. Morse code even made it beyond Earth. Astronauts on early space missions used it for short transmissions, and NASA's Interstellar Voyager probe carries a Morse message on its golden record, the phrase per aspera ad astra, through hardships to the stars, is inscribed in Morse. If the telegraph was the Victorian internet, the telephone, patented by Alexander Graham Bell in 1876, was the Victorian Zoom call, real-time voice chat through wires. Early phones still relied on human code of sorts. You'd crank a handle to alert a switchboard operator, then literally tell them who to connect you to. These operators, mostly women, manually connected circuits. But telephone traffic grew so rapidly that the human link became a bottleneck. Enter Almond Stroger, an undertaker in 1880s Kansas City, suspected the local operator, who was the wife of a rival undertaker, was diverting his business calls to her husband's firm. Furious, Stroger invented the first automatic telephone exchange, a stepping switch contraption that could route calls mechanically, no operator needed. Imagine being so annoyed by a phone operator that you revolutionized the telephone system. But he did, and by 1892, the first automatic dial exchange opened, courtesy of the Stroger switch. That's why today we dial numbers directly. A code, the phone number, instructs the exchange where to route the call. No intermediary meddling. Stroger's quirky feud birthed the automated network that would eventually span the globe. Segment 2. Early networks, from telex to ARPANET. As the 20th century progressed, communications networks multiplied and improved. Telegraph evolved into telex, a global network of teleprinters using a typewriter-like interface, widely used mid-century to send text-based messages over phone lines. Telex assigned every machine a unique address code and was an early form of network addressing, foreshadowing computer IP addresses. Meanwhile, the foundations of the internet were being laid not by visionaries of commerce, but by defense researchers worried about nuclear war. In the 1960s, the US Department of Defense funded Advanced Research Projects Agency to explore resilient communication. The result? ARPANET, launched in 1969, a packet switching network to connect research computers at universities and military sites. Unlike telephone circuits, which created one dedicated line per call, ARPANET broke data into packets and sent each packet independently through the network, where they'd be reassembled at the destination. This was a radical shift. It meant the network could automatically route around damage, a key feature if parts of it were destroyed, say by an attack. ARPANET began humbly, just 4 nodes in late 1969, UCLA, Stanford, UC Santa Barbara, and University of Utah. Fun fact, the very first message on the ARPANET was LO. It was supposed to be login, but the system crashed after sending the letters L and O. Picture this, October 29, 1969, UCLA. A student programmer types at a terminal, L. Over a 50 kilobit phone line, that character travels north to Stanford. Do you see the L? He asks by phone. Yep, got the L, comes the reply. He types O. Got the O, Stanford says. And then the system fails before the G. The first internet message was a 2-letter word. LO, as in lo and behold, a most fitting accident. An hour later, after a reboot, they successfully sent the full LOGIN command. From such baby steps grew a network that by 1973 spanned continents, with a satellite link to Europe. By 1973, ARPANET had about 40 nodes, including one in Norway and one in London. This map of early ARPANET looks modest, a few dozen boxes and lines, but it was the embryo of the internet. Eerily, you can already spot familiar names. UCLA, MIT, Stanford Research Institute, SRI, all exchanging data in a standardized way. Throughout the 70s, researchers like Vint Cerf and Bob Kahn developed the TCP/IP protocols, Transmission Control Protocol, Internet Protocol, that would allow different networks to interconnect, hence Internet, Internetwork. On January 1st, 1983, ARPANET officially switched to TCP/IP, essentially marking the birthday of the modern internet. With a capital I, back then only hundreds of computers were on it. By the late 80s, it was thousands. One early application on ARPANET was electronic mail. The @ symbol in email addresses, user at host, was chosen in 1971 by Ray Tomlinson as a separator because @ wasn't used in people's names and intuitively read as a user at machine. His first email was a test message. Legend says it was likely QWERTYUIOP, the top row of keys, just to fill the buffer. Little did he know he was kicking off a communication revolution that decades later would clog our lives with spam and also keep us more connected than ever. Segment 3. The Internet Goes Public, Wiring the Globe. The 1990s saw the internet explode from academic usage to mainstream. Key moment, 1991. Tim Berners-Lee in Switzerland introduced the World Wide Web, a system of linked hypertext documents accessed via browsers. Suddenly the internet had a friendly face, or at least a blue underlined hyperlink. The number of hosts on the network jumped from under 100,000 in 1989 to tens of millions by 2000. The code making this possible included everything from networking protocols to router firmware to web server software, an entire stack of communication code working in unison. Consider how a simple click on send for a chat message works. Your text is broken into packets by your device's network OS, each packet labelled with destination, the recipient's IP address. Those packets zip through possibly dozens of routing decisions across the world, under oceans via fibre optic cables, through ISPs and arrive, usually in under a second, reassembling on your friend's screen. It's everyday magic, enabled by code that implements things like TCP, making sure all packets arrive and in order, and higher level protocols that ensure your message is private. Encryption again, as we saw in episode 1. Did you know the internet's expansion also owed to code and policy decisions that kept it open? In the 90s, many competing network systems existed, CompuServe, AOL, etc. But the open protocols of the internet, like HTTP for web, SMTP for email, won out, in part because no single entity controlled them. They were built by community consensus, the Internet Engineering Task Force, and free for anyone to implement. This openness was analogous to the open source movement in operating systems. Anyone could write code to join the internet, which fueled innovation. By the 2000s, we began layering wireless on top. Wi-Fi made the wired world also a wireless world in last-mile connectivity. But rest assured, the core trunks connecting continents remain very much wired, high-bandwidth fibre cables across land and sea. The result today is stunning. We have roughly 5 billion internet users. There are over 1.5 billion websites, though many inactive. Each day, hundreds of petabytes of data flow across the network: news, entertainment, personal communications. Social media alone generates unimaginable volumes. It's estimated that in 2025, users will send about 150,000 messages on Facebook every second, and about 500 hours of video are uploaded to YouTube every minute. How does the network cope? Continual upgrades in code and infrastructure. For instance, the introduction of high-speed packet switching routers that can forward tens of gigabits per second, and intelligent algorithms for traffic management. If early ARPANET was a two-lane road, today's internet backbone is a massive superhighway with multi-lane interchanges. One surprising fact is the sheer density of information flow. As of 2022, more than 500 hours of video are uploaded to YouTube every minute. And YouTube's recommendation algorithms, powered by code and AI, drive about 70% of views on the platform. Effectively, algorithmic code is steering a big chunk of human attention globally. Likewise, content delivery networks, CDNs, use predictive algorithms to cache popular content near demand hotspots, reducing latency and bandwidth strain. All these are layers of code atop the basic internet, optimizing and managing the wired world for efficiency and speed. Segment 4, connecting the unconnected and final frontiers. The story of wiring the world isn't done until everyone is connected. We're close, but not there yet. Tech giants deploy low Earth orbit satellites and high-altitude balloons to reach areas where laying fibre isn't feasible. Interestingly, we've even repurposed old-school technology like SMS, text messaging, to carry internet data in places with only basic cell coverage, a sort of code trick that encapsulates emails or web requests into text packets. And code is at the heart of interoperability, enabling an app on a cheap smartphone in a remote area to communicate with a cloud server thousands of miles away often involves compressing data, error correcting against poor signals, and optimizing for minimal power use, all feats of clever programming. Looking up, we also have an interplanetary internet in the works. NASA and other agencies realized that communication with spacecraft can benefit from an internet-like approach. They've designed protocols tolerant to huge delays and disruptions, because a message to Mars might take 20 minutes one way and could be blocked by planetary positions. The software on rovers like Perseverance actually use a form of delay disruption tolerant networking, DTN, basically internet protocols for space. We have orbiters around Mars that act as data relays, store and forwarding rover data back to Earth when aligned. So in a way, the wired world extends off-world. If one day humans establish a base on Mars, rest assured an email from Mars to Earth will route through a cosmic network designed by extending the same principles that connect New York to London today. Think of how far we've come, from Morse code taps that first bridged cities to fibre optic cables across oceans carrying terabits of data every second. From operators manually connecting calls to billions of devices, auto-routing trillions of packets with no human intervention. Code made this possible at every step, encoding our voices, our words, our videos into signals, governing the switches and routers, ensuring errors are corrected and messages kept secure. The wired and wireless world truly runs on these unseen protocols. So, the next time you stream a film or GPS guides you through backroads, take a moment to marvel. A symphony of code is working in concert worldwide to bring you those bits in real time. It's arguably one of the greatest achievements of humankind, a planet knit together by knowledge and code. Up next, Money Matters, code that transformed finance. We'll uncover how bits and bytes now move billions of dollars, power markets, and even create new currencies. Don't miss the financial flip side of the code revolution.